Imagine an AI that doesn't just give you advice, but actually does the work for you. Clicks, types, formats, and completes tasks in real time. Microsoft's Large Action Model, or LAM, is changing the game, turning Windows apps like Word and Excel into your personal productivity assistants. In this video, we're diving into how LAM was built, how it works, and why it's outperforming even GPT-4 in specific tasks. Stick around to see how this groundbreaking technology could revolutionize the way we interact with software. Microsoft's Large Action Model, often referred to as LAM, is designed to go beyond generating text to performing tasks within the Windows environment. This innovative model interprets user instructions, creates step-by-step solutions, and executes them in applications like Microsoft Word, Excel, and PowerPoint. It bridges the gap between text-producing language models and those that interact directly with operating systems. Training and development. LAM's training relies on supervised fine-tuning, imitation learning, and reinforcement learning to equip it with planning and execution capabilities in dynamic environments. Microsoft collected vast training data, including task descriptions and real action sequences from sources like official software documentation, WikiHow articles, and Bing search queries. GPT-4 was used to convert raw text into structured task action pairs, covering topics from basic tasks like changing fonts to advanced ones such as multi-step formatting and form filling. To enhance its capabilities, Microsoft employed a method called data evolving, where GPT-4 added complexity to basic tasks by introducing additional conditions or instructions. This resulted in over 76,000 task plan pairs. However, converting written instructions into executable actions required additional steps, including pairing text-based plans with real inputs like clicks or typed commands in Word. 4 phases of development. Phase 1, plan generation. Microsoft started with a base model, Mistal 7b, teaching it to write coherent plans for tasks like inserting images or selecting fonts in Word. This model became LAM 1, which could outline task steps but couldn't yet execute them. Phase 2, action learning. Using 2,192 successful examples labeled by GPT-4, LAM learned to imitate these sequences. This phase produced LAM 2, capable of generating actionable steps and mimicking expert AI actions like selecting the correct menu item or entering text. Phase 3, self-discovery. LAM 2, attempted tasks. GPT-4 failed to complete, discovering new solutions and contributing 496 additional successful action sequences. Retraining with this data resulted in LAM 3, further improving its capabilities. Phase 4, reinforcement learning. The final phase introduced a reward model, assigning scores to successful +1 and unsuccessful -1 steps. Reinforcement learning optimized decision-making, culminating in LAM 4, which systematically learned from both successes and failures. Performance evaluation. Microsoft tested LAM with 435 tasks in Word, assessing success rates, accuracy, and interface navigation. Over iterations, LAM's performance improved significantly. LAM 1, 35.6% success. LAM 2, 76.8% success. LAM 3, 79.3% success. LAM 4, 81.2% success. Compared to GPT-4, LAM consistently outperformed in task accuracy and efficiency. In live Windows environments, LAM achieved a 71% success rate, completing tasks in about 30-42 seconds each, significantly faster than GPT-4. Integration into Windows and beyond. LAM powers a Windows-based agent called UFO, which interacts with GUI elements on screen to execute user tasks. UFO identifies controls, coordinates, and purposes, providing this information to LAM, which determines the necessary actions. Unlike text-based models, LAM performs real-time actions, making it a powerful tool for complex workflows across applications.
Future directions and challenges. While LAM showcases potential for AI-driven automation, safety concerns arise when AI operates with minimal supervision. Misunderstandings or errors could lead to significant consequences. The team emphasizes robust error checks and user verification requirements for critical steps. Expanding LAM to other platforms like macOS or mobile devices requires collecting new datasets, a time-intensive process. Techniques like transfer learning may streamline this process, but they remain active research areas. Despite challenges, LAM signals a new era of AI capable of executing tasks rather than just generating responses. A step toward broader capabilities. LAM's achievements highlight how specialized training and iterative development can make AI more accurate and efficient for specific domains. As Microsoft explores expanding LAM's scope beyond Office, questions about scalability, accountability, and ethical considerations loom large. The advancements in large action models raise important questions. Are we moving too fast with AI? Or is this the natural progression of technology? Share your thoughts below and visit judyfmarketing.com for online marketing and more.